Hi students, in this class we are going to study the modeling of medium length transmission lines using Pi network. Suppose a consumer needs some 11 kilovolt at the load side. As you know, this transmission lines will take certain voltage drop. So how much voltage should be generated at the source side? Suppose the transmission line takes some 0.5 kilovolt. Now the generator should produce 11 kilovolt plus the drop in the transmission line 0.5 kilovolt. So 11.5 kilovolt should be produced at the generator so that the customer will get or the consumer will get 11 kilovolt. So in order to find this generator voltage, you should know how much voltage the transmission line takes, or you should know the structure of this network. So that's why we study the modeling of transmission lines. Based on the length of the line and operating voltage, we can classify the transmission lines into short lines, medium lines, and the long transmission lines. Now we are studying the modeling of medium transmission lines. Medium transmission lines can be modeled in three different methods based on the position of the capacitor in the line. One is condenser method, in which the capacitor is placed at the end of the line. Then the nominal T method, in which the capacitor is placed at the middle of the line. Then the nominal Pi method, in which the capacitor is placed at both the ends of the transmission line. Now we are going to study the nominal Pi method. Let me draw the transmission lines. Actually, this is a three-phase system, but we assume that it is a balanced system. So the analysis of single-phase system is sufficient when the three-phase system is balanced. The capacitors are placed at both the ends in the case of nominal Pi method. This is our source voltage. The resistor and the reactance of the line. This is the capacitance at one end. This is the capacitance at the other end of the line. So this is the load at the receiving end. This is the resistance of the transmission line. And this is the reactance of the transmission line. The capacitance is C/2 each at both sides. The resistance is R. The reactance is XL. The receiving end voltage is VR. The sending end voltage is VS. The receiving end current is IR. The sending end current is IS. The current through the transmission line is IL. Current through this capacitor is IC1. And current through this capacitor is IC2. If you look at this network, it looks like the letter pi. So that's why we call this network as nominal Pi method and a nominal Pi network. Now IL equals IC1 plus IR. Likewise, this IS equals IC2 plus IL. Now the voltage VR plus the voltage drop across the transmission line equals the sending end voltage. So Vs equals VR plus the drop in the transmission line. We have to find out the sending end voltage from the receiving end voltage. For that, we are going backwards to find the sending end voltage. Now let me draw the phasor diagram. The receiving end voltage is taken as the reference vector. So VR is drawn horizontally as it is a reference vector. Suppose this is the receiving end current. So this is IR. Suppose the current lags behind the voltage by an angle phi r. So phi r is the power factor angle at the receiving side. As you know, IL is equal to IC1 plus IR. This is our IR. Now I have to draw IC1 to find IL. IC1 is the current through this capacitor. The voltage across the capacitor is same as the receiving end voltage. They are in parallel. So this current IC1 should be drawn at an angle 90 degree leading to the voltage, because as you know, if this is the voltage across the capacitor, the current leads the voltage by 90 degrees in the case of capacitors. So the current through the capacitor leads the voltage by 90 degrees. This is the voltage, so this should be the direction of current. It should lead the voltage by 90 degrees. So this is the current IC1. It leads the voltage VR by 90 degrees. So now what is IR plus IC1? It is IL, the current through the transmission line. So this is IL, current through the line. Now we have to find out the sending end voltage Vs. Now Vs is equal to the receiving end voltage plus the drop in the transmission line. We have two drops in the line. One is the drop across the resistor, the other is the drop across the inductor. The drop across the resistor should be drawn in parallel with the current. The current through the line is IL. So the voltage across the resistor should be drawn in parallel with IL. So this is IL into R. The current and the voltage across the resistor are in the same direction. Now we need to consider the drop across the inductor. If this is the voltage, the current through the inductor lags behind the voltage by 90 degrees. Or I can say the voltage across the inductor leads the current by 90 degrees. So this is the current. Voltage across the inductor leads the current by 90 degrees. So this is the drop in the inductor. It is IL into XL. Now VR plus IL into R plus IL into XL. This is equal to Vs, the sending end voltage. So this is our sending end voltage Vs. Now we have to find out the source current Is, which is equal to IL plus IC2. IC2 is the current through this capacitor. The voltage across the capacitor is same as the sending end voltage Vs. In the case of capacitors, the current leads the voltage by 90 degrees. So this is the voltage, direction of voltage. So the current should be in this direction. Current should lead the voltage by 90 degrees. So this is IC2. Current through the capacitor leads the voltage by 90 degrees. Voltage across this capacitor is Vs. Now what is IL plus IC2? IL plus IC2 equals IS. So this is IS. This is the sending end current. Now the angle between Vs and Is can be represented as phi s. It is a sending end perfect triangle. So this is how we find out the sending end voltage and sending end current.